All right, welcome everyone. So in this video, we are going to think about the following example. Here is a 3 by 3 matrix A, which is upper triangular. Its first column is 3, 0, 0. The second column is 2, 6, 0. And the third column is 1, 2, 2. So all of the entries below the main diagonal are 0. This is an upper triangular matrix. And we want to determine whether or not A is diagonalizable. So we are not being asked to find the matrix P that's going to diagonalize A, possibly, but just yes or no determine whether this matrix is diagonalizable. And so step one in this process is to find the eigenvalues. Then we can find the eigenvectors and consider whether we have enough eigenvectors to construct matrix P. So here we just need to really go through the first two steps. And so because matrix A is upper triangular, we can identify the eigenvalues of matrix A just by identifying the diagonal entries. So we have three eigenvalues, 3, 6, and 2. And then we want to go ahead and find the eigenvectors for each of these eigenvalues with the goal of determining whether we have a set of 3 linearly independent eigenvectors. But now I can definitively say that this matrix A is going to have 3 linearly independent eigenvectors without specifically identifying those eigenvectors, because this matrix A has 3 distinct eigenvalues. Lambda equals 3, lambda equals 6, lambda equals 2. None of our eigenvalues have multiplicity bigger than 1. And we've already proven a result earlier that the eigenvectors corresponding to distinct eigenvalues form a linearly independent set. So for lambda 1, there has to be at least one non-zero, non-trivial vector, eigenvector corresponding to it. We'll call that V1. For lambda 2, there is another eigenvector, V2. For lambda 3, there is a third eigenvector, V3. And because these all correspond to distinct eigenvalues in this case, that means I'm definitely going to have 3 linearly independent eigenvectors. Therefore, we know matrix A is diagonalizable, even if we haven't identified what those eigenvectors are. So we see a really nice result here, which we can generalize, which is an n by n matrix with n distinct eigenvalues is going to be diagonalizable. So we had a 3 by 3 matrix in this case with 3 distinct eigenvalues, and that is enough to conclude that A is going to be diagonalizable without even identifying the eigenvectors. Of course, if we want to construct this matrix P, then it would be important to find some eigenvectors for each of the eigenvalues. So we know that if an n by n matrix has n distinct eigenvalues, then it is definitely diagonalizable. For matrices whose eigenvalues are not all distinct, it's a little bit more complicated. So we've already seen a couple of examples where a matrix had a repeated eigenvalue and it was diagonalizable, and we saw an example where we had a repeated eigenvalue and it was not diagonalizable. So in this case, if we have an n by n matrix A and we have distinct eigenvalues, lambda 1, lambda 2, up to lambda p, where now p is less than n. So some of these eigenvalues have multiplicity which is bigger than 1. So when are these matrices going to be able to be diagonalized? Well, it's going to depend on how large each eigenspace is. So for each of these eigenvalues from 1 up to p, the dimension of the eigenspace is going to have to be less than or equal to the multiplicity of the eigenvalue. So if I have an eigenvalue which has multiplicity 2, the eigenspace might have dimension 1. It might be spanned by one vector. It might have dimension 2. We might need 2 vectors to span the eigenspace, but it cannot have dimension 3, 4, 5, or 6. So at most, the dimension of an eigenspace is going to be equal to the multiplicity of that eigenvalue. At worst, the dimension of an eigenspace is going to be 1. So we are going to have a diagonalizable matrix if and only if the sum of the dimensions of all of the eigenspaces adds up to n, which is the number of rows and columns in matrix A. And so this is going to happen if the characteristic polynomial factors completely into linear factors. So imagine, for example, if we had a matrix A, 2 by 2 matrix A, whose first column was 0, -1, and second column was 1, 0, and we want to find eigenvalues for this matrix. So we take the determinant of A minus lambda I, so we get minus lambdas on the diagonal because we're subtracting them from 0, and the off-diagonal entries haven't changed. And here the characteristic polynomial is lambda squared plus 1. So this is an example of a characteristic polynomial which does not factor into linear factors over the real numbers. And we'll discuss next what to do if we have complex eigenvalues. But for now, we're going to say that if we can't factor the characteristic polynomial completely over the real numbers, then it's not going to be diagonalizable. If we can factor it into linear factors, then we also need to make sure that each of the eigenspaces has multiplicity which is equal to the multiplicity of the eigenvalue lambda k. So to summarize, if I have a square n by n matrix A, it is going to be diagonalizable if and only if the characteristic polynomial factors completely into linear factors, and for any linear factor which occurs with multiplicity bigger than 1, then the corresponding eigenspace for the eigenvalue of that factor needs to have dimension which is equal to the multiplicity of the eigenvalue. And so if both of those conditions hold, A is diagonalizable. And if we let B sub k denote a basis for the eigenspace of eigenvalue lambda sub k, then we can take the collection of all vectors in each of these bases, and that's going to form a collection of n linearly independent eigenvectors, which is going to therefore be a basis for Rn. Okay, so to summarize what we've discussed so far about diagonalizable matrices, let's take a look at some of the 3 by 3 examples we've been working with. So if you consider a 3 by 3 matrix A, we looked at this matrix which had column 2, 1, -1, second column 0, 2, 0, third column 0, 1, 0. And we found that this matrix had two eigenvalues, lambda equals 1 and lambda equals 2. And lambda equals 2 occurred with multiplicity 2. However, we were able to find that the eigenspace for this eigenvalue also had dimension 2. Lambda 1, that just occurred with multiplicity 1, so its eigenspace is going to have dimension 1. And since the dimension of eigenspace for eigenvalue 2 plus the dimension of the eigenspace for lambda equals 1 adds up to 3, A is diagonalizable because A was 3 by 3. So just because you have a repeated root, just because you have an eigenvalue with multiplicity bigger than 1, does not rule out matrix A from being diagonalizable. However, it could. So here was an example matrix A which was upper triangular, where the first column was 2, 0, 0, the second column was 4, 2, 0, and the third column was 6, 2, 4. So this matrix had eigenvalue lambda equals 2 with multiplicity 2, and the dimension of that eigenspace was 1. So right away, I can see that this eigenspace dimension was not equal to the multiplicity of lambda equals 2, so this matrix was not diagonalizable. And we also looked at a upper triangular matrix A, which had first column 3, 0, 0, the second column was 2, 6, 0, and the third column was 1, 2, 2. And because this matrix had three distinct eigenvalues, 3, 6, and 2, we know that each of their eigenvectors are going to be linearly independent from each other. So even without finding the eigenvectors, we were able to determine that we'll have three linearly independent eigenvectors. Therefore, this matrix A is diagonalizable.